Alright guys, welcome to Projectile Motion Part 2. This is actually the last video for this chapter of Kinematics. Probably a pretty difficult one, but hopefully you guys can follow along well. Alright, let's look at this. A student jumps off a cliff with the initial velocity, horizontal velocity v, and lands in a pond below at a distance x. Okay, v, x, okay. In the terms of his initial velocity, how fast would he have to jump to land a distance 2x from the base of the cliff? So he first goes at velocity v and lands displacement x. So what we want to do now is we want to get twice as far, and we want to know how much does v have to change by in order to go twice as far. There's a few ways we can do this. We could do this both conceptually or we could do it mathematically. But I guess I'm just going to do it conceptually. But try to do it on your own mathematically if that makes more sense to you. But what we should know is both of these scenarios, they're going to be taking the same amount of time to fall. So even though you may have to go faster for the second scenario, since the velocity initial in the y direction is 0 for both of them, they're both going to take the same amount of time to fall. The next thing we should know is for both scenarios, the acceleration in the x direction is 0 because there's no acceleration in the x direction. The next thing that we know is the velocity is going to be different for both scenarios, and the displacement is going to be different for both scenarios. Okay, one's going to be twice as much. So if we look at this formula here, we have displacement x equals v initial t plus 1/2 at squared. This becomes 0 because acceleration is 0, and we know that displacement is going to be dependent on the velocity times the time. We know time is going to stay the same for both scenarios. But if we want to go twice as far, that means this side of the equation changes by a factor of 2. And we need to make this side change by a factor of 2. And what that means is velocity here has to also change by a factor of 2 in order for both these sides to change by a factor of 2. So that means the velocity has to change by 2, and then that will go twice as far. All right, moving on. Allie and Tommy are cliff jumping into a pond below. Tom simply drops down from the edge, but Allie takes a running start and jumps with an initial velocity of 20 meters per second. As 20 meters per second. As they hit the pond, A, the speed of Tommy will be more. B, Allie's speed will be more. As C, Allie's speed is 25 meters per second larger than Tom. D, they will have the same speed. E, the speed of Allie is larger than that of Tom. Okay, so let's kind of draw these two scenarios. We have Allie here, or we have Tom here, who simply drops straight down like this. And then Allie, who runs, so she's going to drop something like this. Same cliff, so same height. So what we should know is that they're both going to have the same final velocity in the y direction. Okay, so since they both start with the initial velocity of 0, and they both going to fall the same distance in the y direction, they're both going to have the same final velocity in the y direction. However, for Allie, she's going to have a velocity in the x direction when she lands. Okay, it's going to be that same velocity in the x that she takes that running start, that horizontal velocity of 20 meters per second. So we should know that Allie's speed is going to be more because she has both the velocity and the x and the velocity in the y. So it should be more. So it should be one of these. It won't be the same. Allie's speed is larger. The speed of Allie's is larger than that of Tom. The speed of Tom will be more. No, it won't be that. Oh, aren't these saying the same thing? I don't know. Maybe they're saying the same thing. Anyway, but we know it's not going to be 25 meters per second more. And the reason for that is, well, maybe you should have said 20. But the reason for that is because when we find the final velocity, it's going to be a combination of the Vx and the Vy. So we're not just going to add 20 to it. So it's going to be either B or E. I think they say the same thing. What do I have here? All right, E. The speed of Allie is larger. Allie's speed will be more. Okay? All right, look at the next example. Allie and Tommy are cliff jumping to a pond below. Tom simply drops from the edge, but Allie takes a running start and jumps with an initial horizontal velocity of 20 meters per second. As they hit the pond, A, Allie and Tom will reach the pond at the same time. B, Tom will reach the surface of the pond first. Allie will reach the surface of the pond first. So what we should know is, so Allie here, she's going to be running off, and then it's going to be going like this. Tom, he just simply falls down like that. What we should know is that they're both going to have initial velocity in the y direction of 0. Even though Allie gets a running start in the y direction, since she only goes horizontally, the initial velocity in the y is 0. So it doesn't matter how much someone is moving in the x direction, how long it takes to hit the bottom just depends on the y. So what that means is since they start at the same height and their same initial velocity in the y is 0, Allie and Tom will reach the pond at the same time. Wow, A. Getting sloppy here. All right, let's look at the next question. Okay, Jam and Pam throw rocks off a tall building at the same time. Jam throws her rock straight down. Pam throws her rock downward and outward at an angle between the initial velocity of the rock is 30 degrees. Pam throws the rock with a speed twice that of Jam's rock. Which rock hits the ground first? Okay, interesting question. What we should only care about is, since we're looking for how long it takes to hit the ground, we really should just be focusing on the y direction. Okay, so we only care about the y direction. We know the displacement in the y is the same, so it's going to be falling for the same height. But we want to find what the velocity is in the y direction for Pam. Since we know for Jan it's just v, but we want to know what this is. So this is going to be equal to 2v sine of 30. So what we should also know is sine of 30 is equal to 1/2. So what this turns out to be, 1/2 times 2, this just cancels out with this. So we see the velocity in the y direction is the same as Jam's. So they're both going to be v. So they have the same information in the y direction. The acceleration in the y is just gravity. V initial in the y is v for both of them. Displacement in the y is the same thing. So that means the time is going to be the same for both of them. So they hit at the same time. All right. A marble is fired straight up and reaches the maximum height h. The same gun is pointed at an angle of 30 degrees above the horizontal. What is the maximum height that a marble can reach? So let's draw this up. So shot V initial, it goes up like this and reaches a maximum height h. The same gun is pointed at an angle of 30 degrees, so it's the same gun, so it's going to have the same initial velocity, 30 degrees. And then it moves like this. What is the maximum height? So we know that since it's angled, it has to be less, so it can't be e. But now let's figure this out. So we want to, when we're comparing like this, let's call this scenario A and scenario B. When we're comparing like this, we want to write down the equations that we know. So we know for both scenarios we're going to have an initial velocity. Both scenarios we're going to have a displacement in the y. Both scenarios we're going to have acceleration in the y direction and anything else. And both scenarios at the very top, the final velocity in the y direction is equal to 0. Okay. Now, what we want to figure out is, we know in scenario B, the velocity initial in the y is going to be different than the velocity initial in the A. So we want to know, as this changes, the initial velocity in the y, how does the displacement change? That's the main focus. Now, let's look at the equation that has all 4 of these variables, and we're going to see this one. Vfy squared is equal to v initial y squared plus 2a change in y. And again, we want to find out, as this changes, this initial velocity in the y, how does this displacement change? So let's figure this out. We know for both scenarios, the final velocity is 0. And then we have v initial in the y squared plus 2. Acceleration in the y, we're just going to call that g, or I guess negative g. And displacement in the y, that's what we want to figure out. We want to find how this changes when initial velocity in the y changes. Okay, so I'm going to isolate this displacement in the y because that's what we're looking for. So I'm going to put everything on the other side. So v initial y squared divided by, oh, that's going to be negative because I put it on the other side. And then I'm going to divide by negative 2g. So negative 2g, so negatives cancel out, is equal to the displacement. So what I should know, did I do that right? Yeah. So what I should know is this velocity here and this velocity here, this is going to be equal to v initial sine of 30. So this is the same thing as v initial sine of 30, which is just 1/2. So v initial times 1/2. So now what I'm going to figure out is, okay, if we change this initial velocity by 1/2, how is that going to affect how much this side changes by? And then that how much this side changes by is going to be how much this side should change by. So if I change this to be v initial times 1/2, let me change this. So v initial in the y change by 1/2 squared. What we see is this changes, and we're going to square everything. So this is going to be v initial and y squared. And since it's 1/2, this is going to change by 1/4. Okay? Or I shouldn't do 1/4. It should just be 1/4. Okay? Because 1/2 squared is equal to 1/4. So this changes by 1/4. So we see this side changes by a factor of 1/4. Now, in order for displacement to change, in order for this side to change by a factor of 1/4, we know the height needs to change by 1/4 as well. So the correct answer is the height will decrease by 1/4. Okay, I hope that makes sense. I hope that makes sense. If not, watch it again. But that's what we're trying to do. We're trying to see how much does velocity change by and how much does that change the height. There's a lot of questions like this in the AP exam, so I hope you guys get used to this. All right, let's look at this example, another pretty hard one. As a ship is approaching the dock at 0.45 meters per second, an important piece of landing equipment needs to be thrown to it before it can dock. This equipment is thrown at 15 meters per second at 60 degrees above the horizontal from the top of a tower at the edge of the water, 8.75 meters above the ship's deck, as shown in the figure. For this equipment to land at the front of the ship, at what distance d from the dock should the ship be when the equipment is thrown? So this is a pretty challenging problem. There's a few things that you really have to think about. But the first thing that we should try to find out is, first of all, if you throw this at 15 meters per second at 60 degrees, where is it going to land? Okay. Where is it going to land? And what we should know is, since the ship is going to be moving as this goes, this d is going to be more than where it should land. I hope that makes sense. If not, it'll probably make more sense later on. But we want to find out, where is this going to land? So let's just try to figure that out first. So I'm just going to do x and y. Acceleration to x equals 0. Acceleration to y, -10. We don't know what the displacement of x is. That's what we're trying to figure out. The displacement of y, it's going to be falling down -8.75 meters. And we can also find out what the Vx is and the Vy. Vx is going to be half of this, so it's going to be 7.5 meters per second. But Vy is going to equal, let me figure that out. Ooh, I need my calculator. 15 times sine of 60, which is equal to 13 meters per second, around 13. So Vx, 7.5 meters per second, and then V initial y, 13 meters per second. Okay, we see we only have two pieces of information here, so we need to figure out what the time is going to be first. Oh no, this is looking like a hard problem. All right, here we go. So displacement in the y is equal to V initial y t plus 1/2 ay t squared. This is going to be -8.75 is equal to 13t plus 1/2 -10 t squared. And you should see, okay, we're going to need to use quadratic formula to figure this out. So 0 is equal to -5t squared plus 13t plus 8.75. And then -b plus or minus b squared minus 4ac divided by 2a. So let's figure that out. B is going to be -13 plus or minus b squared, 13 squared, minus 4a, -5, C, 8.75 over 2A negative 5. And we should get 2 times, but we're just going to use the positive times. So I'm going to put that all in my calculator all in one shot. But take your time if you need to take your time for this. 13 squared plus 4 times 5 times 8.75. Square root of that. 18.54. And I know this needs to be a positive number. So what I'm going to do, plus 13 divided by 10. And it's going to be around 3.15. I'm going to say 3.155 seconds. Anyway, I'm sure you guys couldn't do it that fast, so take your time as you guys are doing this. Make sure you get that answer, though, as the positive answer. So we know now it falls in that amount of time. Time is equal to 3.155 seconds. All right, now we should find out, okay, what is this displacement of x? So we can find, okay, we have 4 pieces of information. Displacement of x equals vxt plus 1/2 at squared. We know acceleration in the x direction is 0, so this whole thing becomes 0. Displacement of x equals 7.5 times 3.155. And this is going to equal times 7.5, 23.66 meters. So a lot of people might think, oh, okay, this is the answer. The ship needs to be 23.66 meters when they throw this so that it'll be at the front of the ship. However, that's not exactly true because the ship is moving 0.45 meters per second. So what that means is while this package is in the air, it's still moving. And if we want it right at the front, we need to find out, okay, how far back does it have to be the moment it's launched? So we want to find out how much it moves in a time of 3.155 seconds. And that's how far back it goes. So let me do that over here. So we know that the speed of this sailboat is 0.45 meters per second. We know it's going to be moving for a time of 3.155 seconds, and we need to find the distance of that. So speed equals distance over time. So speed times time equals distance, and that's going to equal, 0.45, I'm going to say meters per second. 0.45 times 3.155, and we get 1.42 meters. So hopefully that made sense, but while this package is being thrown, this boat is going to be moving 1.42 meters. So as soon as the package gets thrown, it moves 1.42 meters because time is passing. So it needs to be 23.66 meters away plus 1.42. So if we do 23.66 plus 1.42, we get plus we get around 25 meters. I hope that makes sense. Watch it again if it didn't, because there's a lot of steps to this. This one was pretty tough. Okay. All right, moving on. All right, another pretty tough one. A cart is moving with a constant velocity of 5 meters per second. A pebble is launched from the front of the cart with a velocity of 8 meters per second at 60 degrees. Just as the pebble returns to the level from which it was launched, what is the distance from the point of the cart? So this is a little bit confusing because this cart is moving while this thing is being launched. There's a few ways of doing this problem. There's a hard way and an easy way. But to do it the easy way, you have to know a good amount of physics. So the thing is, this thing is going to be launched, but at the same time, this car is going to be moving, right? So this car is going to be moving when it's going to be launched. And then what we want to find out is how far does it go once it goes to the same spot. How should I do this? Maybe I'll do this simple way. Okay. So a simple way of doing this is, okay, I'm just going to do X and Y. Anyway, try on your own before you watch the video. But what we should know in order to do this the simple way is this cart is moving 5 meters per second. So when we shoot this thing out, whatever it is in the X direction, we would want to add it by 5 if we want to know how far it goes in the X direction. However, since we know that the 5 meters per second is being moved at the same time as this cart is moving, we could almost actually ignore this 5 meters per second and say that it's not moving and just see how far it lands. Does that make sense? Because they're both going to be moving an additional 5 meters per second. So we can just say, we can kind of just ignore this 5 meters per second and just do nothing with it. I hope that makes sense. I'll explain it again later on, but I'm just going to ignore this 5 meters per second for now. So, and then what do I have? AX equals 0, AY equals negative 10. Then I can find what VY is and VX. VX is going to equal 4, and VY is 8 times sine of 60, 6.93. 6.93. So V initial Y, 6.93 meters per second. Vx is equal to 4 meters per second. And then what we're looking for is how far it goes in the X direction. What we should also know is when it returns to the same point, the displacement in the Y is going to be 0, because even though it goes up and down, it starts and ends at the same exact height. So we want to find this displacement in X, but we only have 2 things, but we can find time because that's going to be the same for both. So let's find that. Displacement of the Y equals V initial Y t plus 1/2 AY t squared. 0 is equal to 6.93 t plus 1/2 negative 10 t squared. We don't have to do quadratic formula because this displacement of the Y is 0. So let's simplify this. I'm going to bring this to the other side. 5t squared is equal to 6.93 t. Divide both sides by 5t. So we get rid of the t one of the t's, and we get t is equal to 6.93 divided by 5, 1.39 seconds. And now I know this is 1.39. And now I can find the displacement of the x. So displacement of the x equals vxt plus 1/2 ax t squared. Displacement of x is equal to 4. T is 1.39. Acceleration of x is 0, so we don't have to worry about that. Times 4, and we get 5.5 ish meters, or like 5.6 ish meters. Okay. And that's actually our answer. And again, the reason we can ignore this 5 meters per second is because if we didn't want to ignore it, what we'd have to do is we'd have to add plus 5 to this and say it's going 9 meters per second in the x direction. And then we'd have to find out how much further it goes. But then we would have to subtract it by how, in 1.39 seconds, how much did this cart move up. So since it's going to be moving up at 5 meters per second and it's going to be launched at another 5 meters per second, we can again ignore this 5 meters per second and just say, and we can just say, okay, if we just ignore it, then it's going to be only going 4 meters per second faster in the x direction. Okay, because we're just saying, since they're both going 5, we just ignore that and just saying it's going 4 meters per second faster in the x direction than the cart. I hope that makes sense. If not, I guess make a comment in the YouTube channel. And maybe I'll show a different way or explain a different way for that. All right. And if you want to try the other way, you can then, and you'll get the same answer. Okay. All right. Let's look at this. A projectile is launched from the ground with an initial velocity v initial at an angle theta above the horizontal. How long will the projectile remain in the air? Okay, so let's do this. A projectile is launched from the ground with an initial velocity v initial at angle theta. How long will the projectile remain in the air? Okay, then we're looking for time. Okay, so let's write down everything we know. Again, with all this, we want to write down everything we know. We know displacement in the y is equal to 0. We know acceleration in the y is equal to negative g. We know v initial in the y is equal to v initial times sine of theta. And we know time is equal to time. And why I'm focusing the y direction is because time, how long it's in the air, is dependent upon the y direction. It doesn't matter really what's happening to x, because how long it's in the air is dependent on gravity pulling it down, and that's in the y direction. So now that we have our 4 points, let's find what formula has all 4 of these variables. And we see displacement of the y equals v initial yt plus 1/2 ayt squared. And let's plug things in. Displacement of the y, 0. V initial in the y is equal to v initial sine theta, t is t, plus 1/2 negative g t squared. And now we're trying to isolate for this t. I'm going to bring this to the other side. So 1/2 g t squared is equal to v initial sine theta t. And what I can do, I'm trying to isolate for this t, so I'm going to divide both sides by 1/2 gt, 1/2 gt, and this way I isolate for this t variable because I get rid of one of these t's. So it's going to be t is equal to v initial sine theta, and this t cancels out, so we don't have to use that, 1/2 g. Or another way we can see this, 2 v initial sine theta over g. Okay? Hope that makes sense. Take your time, watch it again if you need to. There's a lot of questions again like this that are only variables in the AP exam. All right, I think last problem here. All right, so made it to the end. Give yourself a pat in the back. Hopefully you're acing this exam tomorrow or whenever you're watching this, we'll see. All right, projectile is launched from the ground with initial velocity v initial at an angle theta above the horizontal. What is the maximum height of the projectile? Okay, so let's see. Let's again draw the problem out. Same kind of problem actually, v initial, theta, except this time we want to find what the maximum height is. So let's see the variables we know. Again, we know the v initial, and we want to find the maximum height, so we only care about the v initial in the y direction. So v initial in the y direction is equal to v initial sine theta. Acceleration in the y, again, is negative gravity. You could even put negative 10 if you want, and then just replace it with g later on. And then, again, we're looking for the displacement and anything. And we know at the very top, the final velocity in the y direction is equal to 0. So now that we have our 4 variables, let's try to see and isolate for this displacement which we're looking for. So we see final velocity in y squared is equal to initial velocity y squared plus 2a change in y. That's the only one that has all 4. And we have 0 is equal to v initial squared sine squared theta plus 2 negative g change in y, which we're looking for. Now let's isolate for this change in y. So I'm going to bring this all the way over. Negative v initial sine squared theta divided by negative 2g is equal to change in y. This cancels with each other, and this we get our answer. V initial squared times sine squared divided by 2g. All right, guys, congratulations. You watched everything. Hope you guys learned a lot, and we'll see, I guess, how everybody does on the test and things like that. So good luck.